Welcome to solverfy.
Hello everyone, today we're doing chapter 19, problem 70. So this is one of the challenging problems, and it says, explain why using one or two equivalents of sodium hydride, which is a very strong base, results in the different products in the following reaction. So with one equivalent, we yield some sort of product reacted with an alkyl halide to get carbon addition at this phenolic alcohol. However, if we use two equivalents of sodium hydride, we get phenolic addition on this alcohol off the hydrocarbon. And why is that? Well, let's see. Sodium hydride dissociates Na plus and H minus. H minus is not happy being H minus. It'd rather much be neutral at H2. So it's going to deprotonate the most acidic proton. And in this case, if you have one equivalent, the most acidic proton is the phenolic proton. So that will yield us with an O minus here, and then we have 1, 2, 3, 4, 1, 2, 3, 4. That yields O minus here, in which if we reacted with this alkyl halide, do an SN2 attack to add that carbon-carbon double bond or carbon-carbon single bond as seen here in the product. But now what about if we use two equivalents of sodium hydride? So if we use two equivalents of sodium hydride, we will deprotonate two acidic protons. We'll deprotonate this one, but we'll also deprotonate the alcoholic proton. So now, whichever one of these is the strongest base or the strongest nucleophile will act as the nucleophile for the next step. So what do we see here? Well, this phenolic alcohol, well, this can actually go through some resonance stabilization to reduce the electron density around this oxygen nucleus, such that we can have a double bond being formed here and moving the negative charge to this carbon atom over here. So we would essentially get a resonance structure that puts a carbanion on this carbon here. And therefore, because we're moving around the negative charge off of this oxygen atom, and we're actually reducing the electron density away from this oxygen atom and towards the rest of the molecule, we're actually losing nucleophilicity of this oxygen anion. However, this oxygen anion over here, there is no sp2 carbons for resonance to occur. This is attached to an sp3 carbon. Therefore, this negative charge is a very hard charge and is very localized on this oxygen nucleus. Therefore, this is going to be much more reactive than this negatively charged oxygen, which can go through resonance stabilization to decrease electron density of this oxygen atom. Therefore, because this oxygen nucleus cannot reduce its electron density away from the oxygen atom, this will be the strongest nucleophile or strongest base, and it will go through the SN2 mechanism to form the product seen in here.